Okay, class, this is number 23. We're supposed to find the area bounded by the line y equals x plus 3 and another curve x equals negative y squared plus 6y minus 7. This second curve is quadratic in nature. I think it's a parabola that opens to the left because I've graphed it before, but the negative coefficient of the y squared term says it opens to the left. So the first thing to do is start by graphing some points. So I graph the points for the line y equals x plus 3, just like you normally would. And then to graph the points for the curve, I noticed that x is dependent on y, so I just chose a bunch of values for y and started plugging those in. So if x is 0, y is 7. I said that wrong. If y is 0, x is 7, negative 7. If y is 1, x is negative 2. You get all of those points. You can see the curve, and there's definitely an area between those two curves. So we'll orient our rectangles horizontally to get one x value minus the other x value as this vertical, I said it wrong, this horizontal distance. The vertical component here of this rectangle, or the vertical dimension, is dy at some incrementally small value on the y-axis. So as we take this rectangle and move that guy around, we might need to stretch him out a little bit. But we're going to wind up with calculating areas of different rectangles. So if I move the rectangle down here, and I need to make it a little bit smaller, I can see that we wind up with some sample rectangle based on a length on the top and a width, or a height of that rectangle, I guess, is dy. So start plotting those out. One thing to note is that we took this original equation and solved for x. That way we have both equations, x equals some expression in terms of y. So when we do x2 minus x1, the curve on the right minus the curve on the left, everything's in terms of y. Do a little simplification there, and then we'll just note that the area of this sample rectangle winds up being just the product of these two quantities. So if I want to add up all of the rectangles, then I use integration. Note that we're integrating from using the intersection points, y equals 1 up to y equals 4. So this just becomes a calculation then. Need to find an antiderivative of negative y squared plus 5y minus 4. So that actually winds up being negative 1/3 y cubed plus 5/2 y squared minus 4y. Evaluate that expression at 4, and then evaluate that expression at y equals 1. Find the difference of those two evaluations. And then we can say, wait a second, this is looking kind of familiar. So numerically, we've got some values here, and this winds up being the same as 9/2. You can pause the video and double check my arithmetic there. But I note that 9/2 sounds familiar. So this shaded area, that's numerically equivalent to the shaded area from number 15. So it's kind of strange that these two areas that don't appear to be related actually wind up having the same numerical value. So it's kind of cool. Hope that helps. We'll see you in class.